This talk in the Building Minds with Patterns series is about the motivation pattern. We will briefly highlight the features of a generic cognitive architecture and discuss design patterns for cognitive systems. Then we will delve into the specifics of the motivation pattern, and finally we will show how this pattern fits into some existing cognitive systems. What is a cognitive architecture? A cognitive architecture is a design for an artificial mind. It is realized in a diagram depicting the elements of the mind that the architects claim are necessary and sufficient to support thinking or cognition. But how do we build such a system in the first place? The answer is simple. We need to establish a list of requirements identifying what the artificial mind will do. Once these requirements are elicited, we can then design a cognitive architecture to fulfill the requirements. So at a very high level, some initial requirements could be that 1. We want an artificial mind to communicate with the device, such as a car, a robot, a smartphone, or an avatar, that is situated in the real world or in a virtual world. 2. The device will send data. We can call this data observations or observables from the world to the mind, and receive commands from the mind. We can call these commands actuations. 3. Some components will think about the observables and infer new information about them. We will call these coordination components. 4. We will need to have the system learn and improve its behavior over time. The system will therefore need to observe its own performance. We will call the components that reflect upon the system's behavior reflection components. 5. We will want the system to stay within its capacity for memory and performance and not get slower over time. So we need to periodically consolidate the information stored in the system, and therefore we need components for that. These 5 basic requirements can be supported in many different architectures. We now present a generic cognitive architecture template. In essence, a cognitive architecture is a blueprint for an artificial mind. Here, we see the areas for observation, coordination, reflection, and consolidation, as well as the device situated in the world. In this template, we can see a device situated in a real or virtual world. This device communicates with a cognitive system through observation components which store input from the device into the system's memory. The observation components are also responsible for communicating with the device's actuators, which perform the actions in the world. We also see that there are coordination components which update the memory with new inferences. The reflection components are responsible for changing the overall behavior of the system. And finally, the consolidation components are responsible for ensuring that the memory does not exceed its available capacity. What are cognitive system design patterns? Isaiah Berlin once said, "To understand is to perceive patterns." In building an artificial mind, it's helpful to start somewhere, and preferably not from scratch. There are a number of cognitive system design patterns which can be used to implement the required mind functionality. Mapping requirements to design patterns can assist in defining the overall mind architecture. Some design patterns are depicted below. This talk's focus will be the motivation pattern. What is the motivation pattern? Motivation is the basis of action for a cognitive system. A system has needs, for example, the need for energy or a strong wireless signal. Needs are homeostatic variable. A homeostatic variable is a variable having 2 values, a target value, which is the desired value for the need, and an actual value, which may differ from the target value. Ideally, the target and actual values are the same, and that state is called equilibrium. An urge, also called a drive, is the delta or difference between the target and actual values of a need. Urges compel the system to create objectives to reduce the delta between the target and actual values. The motivation pattern is useful when the system must balance trade-offs between competing goals, or return homeostatic variables within a device to their target values. A real or virtual device registers its needs and capabilities with the system. The needs are the declared homeostatic variables. a list of identifiers for each need is delivered. And the capabilities are the device's actuations, or things it can do. A list of capabilities is delivered. This allows the system to dynamically add or decrease functionality. The registrar establishes the device as available for use. The registrar may periodically ping the device to ensure it is online and available. So the device sends needs and capabilities to the registrar as a first step. The urges, also called drives, are the delta between the actual and target homeostatic values. For each need identifier, the device continually polls its own internal monitors and sends urges to the perceiver agent. The urges are an observable. The perceiver receives observables from a device and places them in shared memory or on queues. Some of these observables are urges. The perceiver also makes observables available to form the current context or situation of the system. This context is used by other components, such as the action selector. The attention module looks for urges in the shared memory or reads urges from a queue, and uses the urge information to create new objectives to reduce the urge. Or the attention module may reprioritize existing objectives that affect the urge. As the urges decrease, likewise the objective's priority may be lowered. If the urges are at equilibrium, then the objectives may be removed altogether. An objective is a condition identifier indicating some situation that must be achieved or made true. An action selector uses the current context created by the perceiver and the objectives the system is trying to attain to choose the best action applicable to the current context and relevant to the prioritized objectives. The action or actions are forwarded to the executor. Actions are formed from primitive actuations that the device can immediately execute. In addition to the primitive actuation, an action may be a policy, which has a set of preconditions necessary for the actuation to be executed. Or the action may be a macro operator, which contains both preconditions and expected effects, as well as a chain of actuations or sub-macro operators needed for the successful execution of the main macro operator. The executor is responsible for taking an action and sending the actuations to the device. Forces for using the motivation pattern include having the system balance trade-offs between competing goals or returning homeostatic variables within the device to their target values. What is a cognitive system? A cognitive system is a software and hardware implementation of a cognitive architecture. It is an instantiation of an artificial mind. There are a number of cognitive systems that have been researched extensively. Here is a chart of some cognitive systems and design patterns they implement. Cognitive systems which have the motivation design pattern are highlighted in yellow with a red outline on the cognitive systems chart. In order for us to study cognitive systems, we have to align them so that their elements are comparable. The characteristics among cognitive systems that seem important are the ability to perceive information from a device, the ability to be reminded of prior events and situations, the ability to create, retrieve, select, and execute actions. These general regions are depicted in the comparison template, and the cognitive systems we study will be laid out accordingly. Principles of Synthetic Intelligence, or PSI, is a cognitive system created by Dietrich Derner, and the micro PSI cognitive system was created by Joscha Bach. They are both models of human-level intelligence, motivation, emotion, and behavior. The cognitive structures include temporal spatial, and visual representations as components for learning and drive reduction. The impressive part of the PSI system is the explicit representation of psychological, social, and cognitive needs, as well as the mechanisms by which the needs are satisfied. There is no registrar module since the needs are fixed a priori, and multiple components play the part of the attention component. OpenCog by Goertzel and Associates is an architecture for an ensemble intelligence embodying the principle of cognitive synergy. Imitating the brain's diversity of function, the algorithms and structures in OpenCog are designed to work together to exhibit general intelligence. As part of its action selection framework, OpenCog employs a miniature PSI architecture, which encapsulates the capabilities, needs, and drives of the system. IDA, by Franklin and Associates, is an intelligent information processing agent for the Navy in the area of customer service. IDA implements global workspace theory. Its successor, LIDA, augments the architecture and capabilities. Attention is implemented by a focus component. The Autocatalytic Endogenous Reflective Architecture, or ERA, by Nivel, Thoresen, and Associates, is an architectural blueprint for systems aiming at high levels of operational autonomy in underspecified circumstances. ERA implements cumulative experience-based lifelong learning. That is, its knowledge generation happens incrementally and continuously over the course of its interactions with its environment. ERA's foundation is the continuous and parallel creation, execution, and evaluation of small code fragments, i.e. models, that are combined in real time to form programs for hypothesizing about the future from starting states, for example here and now, using these hypotheses to create plans for achieving goals and to hypothesize about causal relations between observed variables and events. For this, the system uses ampliative reasoning, which is integrated deduction, abduction, and induction, which also supports the automatic creation of sub-goals from high-level goals, and runtime sub-goal reevaluation and reorganization, which produces defeasible plans with short, medium, and long-term horizons. ERA demonstrates resilience, can handle novelty, and supports self-reflection through its replicode programming language. ERA is designed for resource management and meta-learning. Resource management is attention, and meta-learning is learning to learn. This system only partially matches our motivation pattern, since it lacks a specific action selector and executor. The drives it has are also underspecified in this diagram. However, the ERA system in itself is a tremendous accomplishment. So to recap, the motivation pattern uses the needs and capabilities of a device to create or prefer suitable objectives that reduce the urges of the device. Devices have predefined needs and capabilities which can be registered with the cognitive system. The device thereafter forwards urges to a perceiver module, which in turn relays them to an attention module. The attention module creates or reprioritizes objectives that ameliorate the urges. Actions are chosen based on the objectives and sent to the device. Forces for using the motivation pattern include having the system balance trade-offs between competing goals or returning homeostatic variables within a device to their target values. You can read more about this design pattern in the book Building Minds with Patterns, available on Amazon. If you found this information useful, please Please like the video and subscribe to the channel, and visit us on Patreon. Become a member so that we can bring you more helpful content. Find us on the web at Linktree. We'll see you in the next video.